In the last video, we have seen two n surfaces. First one was n sphere and second one was n plane. Today we are going to see a third kind of n surface known by the name cylinder over a surface. This surface is constructed from an n-1 surface. We need an n surface. We construct this n surface from an n-1 surface in Rn. So let us start with an n-1 surface. Let S be an n-1 surface in Rn. We know that by the definition of surface, since S is a surface, there exists a function f from U to R, where U is a subset of Rn, such that S is f inverse of C for some real number C, and any point on that surface S is regular with respect to f. Any point on that surface is a regular point of f. This means that for any point on that surface, at least one of the partial derivatives, one of the first order partial derivatives of f at that point is non-zero. So from the definition of surface, we have the existence of a function with the required properties. From this f, we can construct a function g. G from u cross r to r, defined by g of x1, x2, etc. xn plus 1 equal to f of x1, x2, etc. xn. So clearly from the definition of g, we can see that partial derivatives of g are the partial derivatives of f except for n plus 1 coordinate, where it is 0. Since partial derivatives of f are non-zero at all the points other than the origin, the partial derivatives of g are also, at least one of them is non-zero for any point on g inverse c. So we have a function and we have g inverse of c, and for any point on g inverse c, this function g is regular. Therefore, g inverse of c is an n surface, and this n surface is the n surface defined as the cylinder over the surface S. For an example, let us take an n surface. Let us start with an n-1 surface. Here it is unit circle with a center at origin. So from the definition, we can construct a function. If you remember the pattern, f of x1, x2 equal to c is the set f inverse of c. F inverse of c is the set of all points x1, x2 such that f of x1, x2 equal to c. If you look at the pattern, f of x1, x2 equal to c. Therefore, f of x1, x2 is x1 square plus x2 square and c equal to 1. So this is a straightforward construction. But you should remember that for any surface, there exists a function of this nature, but this function is never unique. I can construct functions like, if I take f of x1, x2 equal to x1 square plus x2 square minus 1, then s is equal to f inverse of 0. Again, if I take f of x1, x2 equal to 2x1 square plus 2x2 square, then again s is equal to f inverse of 2. There is also another method of inversion. So scaling, inversion, and shifting. All these operations will give a different definition, a different function, and many different functions can exist. Therefore, the function is not unique, but there exists some function. So let f be such a function. Here we have a function f of x1, x2 is equal to x1 square plus x2 square. Now we can go, okay, we can check whether it qualifies, the regular point condition is satisfied. Gradient of f at x1, x2 is x1, x2, x2, x1, 2x2. And x1, x2 are never 0. x1 not together 0. The center is not there on this circle. Therefore, the gradient is non-zero at all points on this unit circle. Therefore, it is regular. And if you remember the construction, we can define g of x1, x2, x3 from equal to f of x1, x2, which is equal to x1 square plus x2 square. Now, we need to check whether we don't have to check, but we can show that we need to show that to call this a surface, we need to show that all points on this surface are regular points. Therefore, we proceed with the gradient of g at x1, x2, x3. The gradient of g at x1, x2, x3 is x1, x2, x3, 2x1, 2x2, 0. And clearly, the origin is not on this g inverse of 1. Therefore, g inverse of 1 is a cylinder. If you take g inverse of 0, which is the origin, the only point origin on this, which is a set of a singleton set which contains only the origin, but this is not a this is qualified to a surface, and again this is not regular with respect to g. So now we have g inverse of 1 is an n surface. It is a 2 surface in R3 and it is the usual cylinder. And if you look at the image, if you look at the circle, unit circle, we have a red circle in the diagram, and the construction is introducing a new axis x3 perpendicular to x1 and x2 and extending this surface along this axis. This circle is extended in either direction to get a cylinder. So this is a cylinder of infinite length, infinite height. Now we are coming to the exercises. In exercise 4.5a, the question is to sketch f inverse of 0 given f of x1, x2 is x1. If you change f into g, that is, draw g inverse of 0 where g of x1, x2 is equal to x1, you can understand that there is a function f such that f of x1 equal to x1. This is nothing but the red line shown in this image. In the x1 axis, f of x1 is x1 itself. And how do we construct the cylinder? We are introducing a new axis x2 and extending this line in either direction of x2. Now, then we get a plane of infinite length and infinite breadth. Now coming to 4.5b, the question is to draw f inverse of c where f of x1, x2, x3 is x1 minus x2 square. Again, if you change f into g, the question is to draw g inverse of 0 where g of x1, x2, x3 is x1 minus x2 square. Then we have a f of x1, x2 equal to x1 minus x2 square. This is the original surface, and from this surface we are constructing the function in the question, which is the function which defines the cylinder over the surface S given by f inverse of c, the newly defined f inverse of c. We have changed the f in the question to g and we are defining a new f. Now we can see that f gives a surface. This surface is an n-1 surface, and the new g obtained by renaming f is the n surface. So f of x1, x2 equal to x1 minus x2 square gives a surface. F inverse of c is the parabola shown in the second diagram, the red u or the parabola. And if you extend this parabola in the direction of x3, you will get a u-shaped plane, a bent plane. And coming to the third exercise, 4.5c, the question is to sketch f inverse of 0 where f of x1, x2, x3 is x1 square by 4 plus x2 square by 9 minus 1. Again, if you are following the same pattern, we can start with the function f of x1, x2 is x1 square by 4 plus x2 square by 9 minus 1. And this function is the ellipse drawn in red, the third image, in x1, x2 plane. It is an ellipse with radius 2 in x1 axis and radius 3 on x2 axis. And if you extend this ellipse along x3 axis, you will get the cylinder, which is what is demanded in the question. And coming to 4.6, cylinder over the graph of f of x is equal to sine x. If you draw the graph of sine x, you will get the red curve. You can extend this curve if you want to. And this is the graph of sine x in R2. We are introducing an axis x3 and extending this graph of sine x in either direction. Then you will get a plane bent as a sine curve. These are the sketches demanded by the exercise. Now we are proceeding to the fourth class of n surface, which is the surface of revolution obtained by rotating a curve about an axis. So here we start with a curve. We start with a curve in Rn plus 1, and we rotate this curve about an axis to get an n surface. So curve is f inverse of c. Again, f is a function from u to r, where u is a subset of Rn plus 1. And for each point on that domain, del f of p, or gradient of f at p, is non-zero. And we need one more condition to rotate or revolve this curve about an axis. This curve should not touch that axis. If it touches, the condition is going to be different. Therefore, it should not touch the axis, and it should be on one. It's better to be on one side of that axis, on the positive half plane or negative half plane. Okay, given by that axis. So this is a curve on x2 greater than 0. Now here we are taking, for example, we are taking a curve with domain of f greater than on the positive x2, or x2 greater than 0 is the x2 greater than 0 is the open subset of R2, and we are taking u as a subset of this open set, and we are defining a function on this u, f from u to r, and gradient of f at any point on this u is non-zero. And we are defining C as level set of f inverse of C. So we have a curve. And what we are going to do is, from this curve in Rn, we are going to, from this curve in Rn, we are going to construct a curve in Rn plus 1. Sorry, yes, an n surface in Rn plus 1. So this is done by rotating this curve about the x1 axis. You can imagine like this is sine x is drawn. Suppose you are attaching a stick from origin to this curve and rotating about this point. If you are fixing the origin and rotating this about x1, you will get a bowl shaped, a bottomless bowl. Okay, both ends are open. So how do we write the function and the surface? From f, we can construct a function g from u cross r to r, where g of x1, x2, x3 is f of x1, comma, x2 square plus x3 square root of x2 square plus x3 square. If you look at this expression, instead of f of x1, x2, we are introducing a circle for each point x1. For each point x1, f inverse of c, f inverse of c is going to contain a circle such that for each x1 there exists a circle with a fixed radius which is equal to x2. Earlier, we had only a point. For each x1, we have a point on this red curve. On the sin x, we have a point, and this is the only point with respect to x1. Now, when we are constructing G, we are drawing a circle about that point on x1 axis with that length. So this is done by this definition. By the definition of G, we are drawing a circle with the distance of x, the point, the distance on x2 axis, with the radius as the distance on x2 axis. Now we get a surface. G inverse of C is an n surface. We can take a simpler example. If you go to the exercise, we can see that in exercise 4.1 minute. In exercise 4.8a, the exercise is to sketch the surface of revolution obtained by revolving x2 equal to 1 about x1 axis. So x2 equal to 1 is a straight line parallel to x1 axis at a distance 1 unit from origin. And if you rotate this line about x1 axis, you will get a cylinder. Each point is at distance 1 from x1 axis. Therefore, at each point on x1 axis, you can draw a circle with radius 1. And combining all these circles, you will get a cylinder. And coming to the second example, 4.8b, exercise 4.8b, the exercise is to sketch the surface of revolution of the curve minus x1 square plus x2 square equal to 1 for x2 greater than 0. x2 square minus x1 square equal to 1 is a hyperbola. And this hyperbola contains two arcs, one in the positive x2 plane and second in the negative x2 plane. We need only the curve on positive half plane. So the other plane is drawn in dotted lines. So we take the hyperbola, part of hyperbola on the positive x2 plane, and we are revolving this hyperbola about x1 axis. The difference from the first example is that this hyperbola is at a different distance from x1. For each x1, the distance, the corresponding x2 is at a different distance. And we are drawing a circle of that radius. Thus, we get a hyperboloid, one-sheeted hyperboloid. With at the origin, it is going to be a circle of radius 1, and it increases. The radius increases as we move away from the origin in either direction. Coming to the third example, 4.8c. The exercise is to sketch the surface of revolution of the curve x1 square plus the square of x2 minus 2 equal to 1. x1 square plus x2 minus 2 square equal to 1. This is x1 square plus x2 minus 2 square equal to 1 is a circle on R2 plane with center 0, 2 and radius 1. This circle, we are revolving this circle about x1 axis. Therefore, we get a torus. So these are the three sketches demanded in the exercise. Now, in the next video, we will be seeing a theorem which suggests that suppose there is a surface and it has an extreme point. The surface has an extreme point. If you take this torus, there are points which are extreme. There is no point after this 2. from origin. If you take line, draw a line from the origin, there is no point further from that point. Okay, you can think that as an extreme point for simplicity. So if you take extreme points, then the normal at that point is the scalar multiple of normal of any curve at that point. The curve should be on that surface. If you draw a curve on that surface through that point, the normal of the curve at that point is going to be a scalar multiple. It is not going to be the same, but it will be some scalar multiple of that curve. Now, I will use 3D models I have drawn some 3D images for these exercises, and it is updated on our blog. I will show that for the first. Okay, so this is our blog. If you click on course material, it will lead you to differential geometry 3D models. Okay, exercise 4.4, 4.5a, 4.5b, C, 4.6, 4.8a, 4.8b, 4.8c. So if I will show a 4.8c, for example, 4.8, if you click on that, it will generate a page. It will show. So this is the circle we have drawn. This is of radius 1 centered at 0, 2. And if you rotate this circle about x1 axis is through this point. So x1 axis goes through the middle of this torus. So if you rotate this, you will get a torus. Okay, you can visit this page for 3D images. And in the next class, we will be seeing